So now that the modeling with Tephra is finished, it's time to do probability calculations. Okay, and really what we do is a frequentist approach. In this case, we want to express what is the probability of exceeding an accumulation greater than a critical typical accumulation. So let's say in the case if we had run 100 simulations, okay, and we want to assess the probability at a given point to exceed an accumulation of 10 kilogram per square meter. For this given point, we would load our 100 separate simulation and see how many times this threshold of 10 kilogram per square meters was exceeded, okay? And if I have exceeded it 40 times, it means that I have 40% probability of exceeding this 10 kilogram per square meter. Okay, so remember that in this case we run only 25 simulations, but we typically run more than 1,000. Okay, so let's go to the post-processing menu, and you see that we have three options: probability calculations, hazard curves, and probabilistic isomass maps. And it is critical to do them in order, else you're gonna display errors. Before doing that, I just want to show you this preference menu here. And in this preference menu here in the probability calculation panel, you have a vector of values which corresponds to the accumulation, Tephra accumulations, for which you're going to calculate probabilities. Okay, so here this is 0.01 kilogram per square meter, this is 10 kilogram per square meter, up to 1,000 kilogram per square meter. So if you want, you can customize that. We're also going to calculate typical isomass maps for a given probability of occurrence. Okay, this is discussed in details into the papers and the user manual, but this is typically more useful to calculate pre-event impact assessments. But here in this case, we're going to calculate isomass maps for probabilities of 10, 25, 50, 75, and 90%. Then on this panel, you can display you can customize some map displays anyway. So let's start with our post-processing. So I'm going to first start by computing probability matrices over our grid of calculation. So if you had calculated, if you had run your model on only points of interest and not a grid, you wouldn't be able to use this probability calculation and this probabilistic isomass maps function. You would be only able to use the hazard curve function. But in this case we did, so let's go get our run. Let's take the 2000, okay, the 2000 type eruption long lasting, okay, and then I choose this and I load it. So okay, I run it already, so never mind. So the first operation that it does, it's gonna sum the contribution of all my single long-lasting eruptions. So remember, we set an eruption that was lasting between 24 and 30 hours, okay, and this eruption was sliced into 6 hours periods. So if I go to the output folder, outputs, I see that for a single run, these are my 25 eruptions that I've simulated. I have 5 different outputs. Okay, so the first operation that the code does is it sums them into one single output. So it takes the contribution of all the 6 house bits and sums them into one file. Okay. Then after summing, it goes through all this summed file, retrieves the maximum accumulation, reads all the points, and then on all the points calculates the probabilities of exceeding all these Tephra accumulations. Okay, and these final calculations are stored in the prob folder of your project, and the probability calculations are available in different shapes. So for example, there's a column shape. So if I go here and I load that, This is my probability using all wind, the wind population, the probability of exceed an accumulation of 75 kilogram per square meter. And excuse me, before this fourth column, when I was doing the output, single outputs of the model was a Tephra accumulation. Here, the fourth column is a probability to exceed a value of 75 kilograms per square meter. So this type of output is useful, for example, if you use plotting codes like GMT or the Python library basemap. But this probability is also available in various formats, such as, for example, this is a typical ArcMap raster, which you can directly import in ArcMap for further calculations. And then there's this mat folder, which are the files that are used by TephraProb for further calculation and mapping. Then the second thing we want to do is to calculate hazard curves. Okay, so the first thing that is prompted is again to go get the run file. Okay, and the second thing that it asks you is to get the point file where we define our points of interest where we want to calculate hazard curves. So we go to grids, and it was coordinate points of interest, and we load the point file, loads the file, and calculates for Angostura and Villa Traful as we asked. And the output of the curves is located somewhere different. It's located at the root of the TephraProb folder. You have this curve folder here, and this is where our curves are stored. Okay, the data for the curves. Simply because by putting them here, we can, if you do, for example, different runs for different types of eruptions, then in the end you can plot for a single point of interest, for example, curves for various eruptions, or anyway, I'll show you that in a tiny bit. And then the last thing you can do is do your probabilistic isomass maps. Okay, so the same, you come get your run file, you get your run file, and then it's calculating. It gives, while we're doing some interpolation, sometimes you have some warnings, but that's not very a problem. So finally, you are ready to just look at the results of your simulations. And so this display button here, you have 4 different options. So you have a display figure. So this is if you want to display within MATLAB. So if I go to my run here, you have this figure folder, and the figures are saved as EPS vector format, but they also are saved in the MATLAB figure format. And so if you want to customize the figures, you need to open them using these functions, because they are set by default to be hidden. So if you come here and you open them, it's going to show them, and then you can modify them the way you want and re-export them in whatever format you prefer. Then the probability maps. So if I go get my probability maps here, I need to reselect my run. Okay, and here I have this window that opens, and these are all the probability calculations that were done for your run. And you have all dry and rainy for the seasons, and then you have probabilities of 1, 10, 100, and 1000 kilogram per square meter. Okay, so let's say that first I want to display probabilities of 1, 10, and 100 kilograms per square meter. I just select them, I press OK, and the plotting occurs. And these are the results. Okay, so for 1 kilogram per square meter, 10 kilogram per square meter, 100 kilogram per square meter. Okay, and you see that these lines are not very smooth, and that's just because we didn't run enough simulations. Okay, and these maps show you the probability of exceeding a Tephra accumulation between 0 and 1, 0 and 100%. Okay, so then another useful thing that you can do is, for example, if you knew you had a seasonality, you might want to just plot, let's say, for example, 10 kilogram per square meter for all the dry season and the rainy season. You click OK, and your maps appear. And here, for example, some places around the world, you have just 180 degrees shift in wind direction, which would be reflected here. So that's one thing. The second thing is then isomass maps. Okay, so the same, I come get my run file here, and now the same as before, I have for all dry season, rainy season, and probabilities of occurrence of 10, 25, 50, 75, and 90%. Okay, so let's plot, for example, for all the 10, 50, and 90% probability maps. And now just be careful that it doesn't show any more probabilities. It shows Tephra accumulation in kilogram per square meter. Okay, so for this eruption scenario, these are the typical Tephra accumulations that you would obtain for probabilities of occurrence of 10, 50, and 90%. And now the last thing that we can do is display hazard curves. And in this case, we don't need to get the run files, we just load the files that we have here. So for example, if I want to show for the difference between old season, dry season, rainy season for Villa La Angostura, I just select them, click OK. And then here it displays the exceedance probability, well, the probability to exceed a given Tephra accumulation. Okay, so in this case, for example, if I consider the dry season and an accumulation of 1 kilogram per square meter, okay, I'll see that I have about a 20% probability of exceeding that, which goes up to 40-50% for the dry season here, for the rainy season here, pardon me. Okay, and then this is also useful, for example, if you want to compare the hazard that there are in two towns. Let's take the all season for both, and Villa Traful and Villa La Angostura, and I can click here, and then this helps me to compare the hazards between both. For the same eruption, the hazard in two different locations. So in the end, I hope you found this video tutorial helpful, and I hope you're gonna find a use in this code. Again, the bonus points with this is that it helps you really automatize loads of the process that you would have to program by yourself otherwise. But one risk using that is to feel self-confident in the code and don't understand the processes behind and use that as a black code. I mean, we use this stochastic sampling in order to help completing the knowledge that we have of the volcanic system. It's not here to create data, it's not here to create a level of knowledge that we don't have. It's really a support for the knowledge that we have. So I encourage you, these are quite basic concepts, statistical concepts, so just check it out, check the user manual. If you have any question, don't hesitate to send me an email. If you have any suggestion, we're really happy to get you know, just like feedbacks from the users. And again, just check the output files, nothing is overwritten. Enjoy yourself, just trying some various parameters, see how the sampling is performed. I mean, just like don't hesitate for a same run to do several attempts to see what's going on. Really just like experience the program, and yeah, if you, well, we hope that this was helpful, the code was helpful, and we hope that's gonna help some people who have no interest in programming skills to do some cool hazard assessments for some cool volcanoes in some cool regions of the world. So cool. Bye.